Hello everyone, we are Team 25071 with our Senior Design Day project involving the extraction of valuable salts from produced water. Going from left to right of this team photo, we will introduce ourselves.
Hello, my name is Brendan Terry.
I'm Dohon Kim.
My name is Victoria Franco,
I'm Silas Diaz.
and we all major in chemical engineering.
Before diving deeper, here's our project poster. At the top left, you'll find the project introduction and statement. Below that are the economic results, including annual revenue, cost, and IRR. To the right are our process and block flow diagrams. Now let's walk through our design.
The main objective of this project is to design a process that extracts enough valuable minerals and salts to offset the cost of pre-treated Permian Basin brine water from a fracking site. This overarching task is followed by finer details of what the project should consider and achieve at its end goal. These include the location of the process plant being in New Mexico. The initial flow of brine water is 25,000 barrels per day to be managed, a final disposal cost of $3 per barrel compared to industry average of $5 per barrel, and lastly, the residual or waste stream is less than 250,000 parts per million of concentrate.
The base theory behind this process is the use of a salt solubility limit. Each salt has a specific solubility before the solution goes into a supersaturated state. In this supersaturated state, ions reform into their salt crystals. With salt solubility being dependent on temperature, two primary methods for forming salt crystals are to boil or freeze the water. For our situation, boiling is more favorable than freezing due to New Mexico having a hot climate. To be able to properly simulate this, we use Aspen Plus's electric NRTL model, which accounts for non-randomness interaction between different molecules in liquid mixtures, which is important for our process as salt ions have non-random interactions. For our design, we created 5 process lines, 2 of which are backups, giving a total equipment count over 200. Our process can be split into 2 parts, initial salt separation and then purification. This split happens at the first centrifuge. Starting with the initial salt separation, it is accomplished by boiling off a portion of the water to move the solution into a supersaturated state. Once in a supersaturated state, the salt crystals begin to form and after a few minutes are sent through the centrifuge to be removed from the system. After the salt crystals are removed from the main process, they contain impurities. As such, they go through a purification process. While each salt's purification process is slightly different, they mostly use the same methodology. Starting with introducing new liquid into the system. For sodium chloride and potassium chloride, this is water, while for the remaining salts, it's ethanol, as ethanol has different solubility limits than water. The new solution is then sent to a centrifuge to remove the salt impurities, followed by being heated in the furnace to vaporize excess liquid, leaving the salt at a 99% or greater purity. With the processes creating large amounts of vapor, we recycle this vapor to heat the feed stream. By recycling this vapor, we can reduce the natural gas requirements of our total system. Moving into the ethanol recovery and waste removal, this part of the process is identical for both ethanol recovery and waste disposal. However, the only difference being waste is sent to a saltwater injection well, while ethanol is sent back to its storage tank. This is done by combining their respective streams before cooling off to their required temperatures. For this process, we have both energy and purification requirements. For energy, we use natural gas as our heating. For cooling, we have a preferred source of cooling water. However, an alternative is proposed later on. And for electricity, we simply get it from the grid. For process requirements, we have both ethanol and processed water for purification. And for maintenance, we have hydrochloric acid, with the respective usages on the right side.
With such a robust, complex system that is designed to operate 24/7, it is crucial that a robust maintenance plan is applied to it. Considering an industrial standard of pricing 11.5% of CTDC, cumulative total distribution costs, towards maintenance, we overcompensate this to 20% for aspects that are beyond our design scope. If there were the case that one or more main lines were to go down and all needs to be shut off, there is a surge tank designed into the process plant in which it can contain the entire process flow for 2 hours. This initial 2-hour time period is an estimation that can be increased depending on how many lines are down in their respective locations. Lastly, to prevent corrosion, scaling, and breakage to equipment, a routine cleaning is essential to maintain the quality results and usage of the unit operations. Therefore, the cleaning agent of hydrochloric acid, HCl, is integrated for a routine cleaning of at least once a week. While further details of scheduling are out of our scope to design or research, we were able to cost the requirements of HCL based on HCL and water purchases that are needed to meet such requirements. This can be seen in the table. While it is important that this project's objectives and tasks are met, it is also crucial to be well balanced and considerate of the sustainability aspects that are integrated, a large one being an alternative to cooling water usage as a part of utility and energy requirements mentioned previously. This alternative being the usage of refrigerant because in the case of water becoming scarce in New Mexico, this alternative requires no water usage and potential hazards can be mitigated with additional safety protocols. Both calculations of their respective CTDCs, maintenance, and yearly total costs can be seen in this table. Lastly, it's an important aspect of our design process that not only is it successful and profitable, but it also can have a positive impact and effect on the community surrounding it. Thus, we have designated 10% of the pure water byproduct at the end of the process line to be contributed towards agricultural use. On top of this, it will be given completely free, and this percentage has the potential and flexibility to increase over time.
With a total of 234 pieces of equipment, we analyzed the logistical needs for optimal plant operation, including the required number of operators and supervisory staff, which came out to be 700 total employees. Wages were determined to increase by 30% up to 50% once a plant manager. The estimated annual labor cost, including salaries, benefits, paid time off, PTO, and coverage for employees on leave, rounds to a value of $117 million annually. The system is designed to operate with either cooling water or refrigerant. Below is a cost breakdown comparing both options. The plant generates $653 million in annual revenue with an estimated maintenance and CTDC for each cooling method. While refrigerant-based cooling incurs slightly higher utility costs, water cooling results in a more favorable internal rate of return, IRR. For reference, an IRR between 30 and 40% is considered strong for new industrial investments. The graph shown illustrates the total discounted value at a 20% rate over a 13-year period for both cooling methods used in our plant. This represents the present value of future income, accounting for the time value of money. The first 3 years are dedicated to construction, with years 4 through 13 reflecting the projected revenue generation. In total, the plant is estimated to gross nearly $400 million over this period.
We achieved our process to get annual revenue of $653 million per year with IRR of 44% and keep residual brine water below 250,000 ppm. Sustainability was a key point. Our design includes a water-based cooling system to reduce costs and allocate 10% of treated water to agriculture at no cost. Last but not least, plant will create 700 jobs in community, supporting local economy while addressing industrial usage. In conclusion, this project derived more than technical success. It provides long-term value through clean water recovery, economic strength, and community support. It's a forward-thinking solution ready to bring environmental and economic benefit to New Mexico and beyond.